Okay, so at this point we've already talked about how to find the derivatives for a product of functions, a quotient of functions, and a composition of functions, where we just learned about the chain rule. And so at this point we're going to continue to develop skills in finding derivatives for different kinds of functions. In this case, we're going to assume that y is a function of x. However, it's not going to be explicitly defined in terms of x. And so what I mean when I say explicitly defined is if I have a function that I could write as y equals something, then that's an example of an explicitly defined equation. But in this case, we're going to be writing an implicitly defined equation. And implicitly is when we have something that, again, we're still assuming y is a function of x, but I don't have to necessarily write it in terms of y equals. In this case, I can have x's and y's be shared on either side of my equation. So in this example, I'd like to start with more simple examples just to demonstrate the process. It is possible for you to rewrite this in terms of an explicit equation, y equals. So if you wanted to check your work at the end of this example, you could take the derivative with respect to x on both sides and double check your answer. However, there are many cases where using implicit differentiation, which is finding the derivative when we have an implicit equation, can save us time and be more useful. So I'm going to start over here, and just like I usually do, I'm going to take the derivative with respect to x of both sides. So in this case, I have x squared plus y squared on the left side, and then I have the derivative with respect to x of 25 on the right side. So x and y are both variables. When I'm taking the derivative, I can take the derivative of the individual pieces. This is a sum. So I have the derivative with respect to x of x squared plus the derivative with respect to x of y squared. And then the derivative of a constant number is just going to be 0. So the derivative with respect to x of x squared, this is something that I already know how to compute. But again, I'm going to hone in on this one unknown here, right? This is asking me to take the derivative with respect to x of y squared. Now, this is something that I don't know how to compute yet because this is in terms of x, but y squared is in terms of y. So what I'm actually going to be doing here is I'm going to utilize basically the chain rule, and I'm going to rewrite my derivative with respect to x as the derivative with respect to y times the derivative of y with respect to x. And notice here that if I viewed these two things as like operations, I could cancel out the dy on the top and the bottom, and I'd be left with d over dx. So I know that this would be an equivalent statement. So if I were to rewrite what I already have, I'm going to keep this the same for now. I have the derivative with respect to x of x squared. And then instead of the derivative of x, I'm going to write the derivative with respect to y of y squared, and then times the derivative of y with respect to x. So again, I know that this statement is equivalent to the derivative with respect to x, so I know that I haven't changed the function at all. However, now that this is written in terms of y, it will allow me to take the derivative of y squared. And then this was still 0 on the right side. So now that I have everything accounted for, I can go ahead and take the derivative. So the derivative with respect to x of x squared is 2x. The derivative with respect to y of y squared is 2y. And then I still have this derivative of y with respect to x. And then on the right side, I have 0. So we're almost finished. The last step here is going to be to solve for dy dx. So I want to move everything to the other side except for dy dx and keep that on the left. So I'm going to move that over here. And I have, let's see, I'm going to keep this here. 2y dy dx is equal to negative 2x. And the last step here, if I wanted to solve for dy dx, would be to divide both sides by 2y. And dy dx is equal to negative x over y. So there we have it, our first example of using implicit differentiation to find the derivative of an implicitly defined function.